Okay, here we are, video number 2. This one should be pretty quick because I want to meet and talk about tomorrow's assessment and what to expect from that and how to turn homework in. So let's get into this. This is section 2.2 from the book. It's about separable first order equations. And now we're allowing linear and, well, nonlinear, really. So nonlinear. Okay, so we're because if it's linear, we know exactly linear first order. We know exactly what to do. We use what we used in 2.1, and it works all the time. So here's how we're going to start this. Any first order ODE can be written in the form dy dx. I'm using x now instead of t, just so we don't get too comfortable with our independent variables. So dy dx can be just some function of x and y on the right. And these x's and y's can be multiplied together. You can have higher powers of y, which makes it nonlinear. So this includes linear and nonlinear ODEs. If it's linear, use the stuff from 2.1. If you're not sure, or you definitely know that it's nonlinear, then this is your second mode of attack, as you might think about it. So now I'm going to do this a little different than the book because not everyone has Calc 3, but if we rewrite, we're going to rewrite the ODE in the form. So we're going to take all the terms in the ODE that don't have a y prime attached to them. They could have x's, they could have y's and y squareds and 1 over y's. And then we're going to separate out all the terms that have a y prime and set all this equal to 0. So when you're looking at the world of separable equations, this is the standard form. Okay? This is the standard form. Okay, now, if you had Calc 3, and we'll come back to this later because we still need to do this, but if you take the y partial of m and it equals 0, and if you take the x partial of n and it equals 0, then the ODE is separable. Okay? And it's separable. In which case, this is what you do. You subtract the m from both sides, and what you get is the n function times y prime, which I'm going to write as dy dx. Okay? Okay, so then multiply, so move the dx over to the left-hand side here. So we have m sub xy dx equals n sub xy dy. And now because the x partial of n, so this is, so since the x partial of n is 0, that means there are no x's here, so I have n sub y only. All right, there's no x's on the right-hand side. And since the y partial of m is 0 on the left here, I only have a function of x. And so what we have now, we've quote unquote separated the variables. This is a function of y dy, and this is a function of x dx. So you integrate both sides. And now I have the integral of m sub x dx, which is a well-defined integral because everything's in terms of x. And over here I have the integral of n dy because everything's in terms of y. And then what do? You solve for y. Okay? And so in this case, we say the equation has been separated. You also use separation of variables for partial differential equations, which we won't do in this course, but it's a really powerful technique. And the hardest part is that you have to do some massaging and manipulating of the function to get it into a separable form, and if it doesn't work, then it's not separable. So let's look at let's just look at a couple of examples here. Actually, let's just look at one, and then we'll do some more in class. What do I have here? Okay, here's the ODE minus 6x y squared plus y prime equals 0. So it's already in standard form, and I'm going to make this an IVP. Y of 1 is 1 over 25, and so we're looking for the solution to this ODE. Now, first of all, is it nonlinear? The answer is yes, because of this term. Okay, and hopefully you see that. I'll explain it to you if you don't, but you should be able to note that because of that term, it is not linear, so it's nonlinear. So now the next question is, okay, what is m sub xy? It is minus 6, come on, Pullman. Minus 6y squared. And what's n sub xy? Well, it's 1. Okay, now note, having it written this way, what do we have? We have, let me look at my notes again here. M sub y equals minus 12xy. And then sub x equals 0. So right now it doesn't look like it's separable. Okay, so these definitions, it takes more massaging. It's weird. Okay, so basically what we want to do here is try and get this thing separable or separated. So I'm going to rewrite this as dy dx equals 6xy squared. Okay, so I added plus 6xy squared to both sides of this equation above. Okay. All right, so here's where the massaging happens. Just look at that. If you leave the 6x on the right and you move the y squared over to the left, you have 1 over y squared dy equals 6x dx. And now we separated. Okay. All right, now let's integrate. Integrate the left-hand side and the right-hand side. So rewriting this, I have y to the minus 2 dy equals integral of 6x dx. So when you integrate the left, you get minus y to the minus 1 plus c1 for that constant of integration. And this equals what? 3x squared plus c2. Right? Because you integrate the x, you get x squared over 2, and that cancels out. All right. And so, because people always ask about this, okay, so I'm going to bring that constant on the left over to the right, and then I'm going to let this constant just be c. So I have y, I'm going to let it be c3, actually. So now I have minus y to the minus 1 equals 3x squared plus c3. Okay, I'm solving for y here, so now I'm going to multiply through by negative 1 on both sides of the equation. So I get 1 over y equals minus 3x squared. So minus c3. which is just a constant. So I'm going to let minus C3 equal C. All right. So now I have 1 over y equals minus 3x squared plus C. And what does y equal? Y equals 1 over C minus 3x squared. And this is our general solution. Okay, and now we find the particular solution. We plug in 1, so we have 1 over 25 equals 1 over C minus 3. Which says C minus 3 equals 25. And so C equals 28. So the particular solution is this guy. All right, see you